Is my screen visible to all of you guys?
Yes, sir.
Okay. So, welcome everyone to the week 12 discussion of this course, Introduction to Machine Learning. And this course was originally taken by Professor Balaraman Ravindran, Professor and Head of the Department of Data Science and Artificial Intelligence, IIT Madras. And myself, Ayan Paul, I am a PMRF Research Scholar from IIT Kharagpur. And my duties are I am a PMRF TA for this course. I will be discussing some of the questions with you so that whenever you will be doing the assignment, you will not feel very alienated. Okay, so that is my duty. But before that, what I want is to discuss some of the theories related to this week so that it will be more clear to you. Okay, so so yeah. Yeah, so last 2 weeks we have discussed about unsupervised learning. Okay, so unsupervised learning, what we have discussed regarding clustering. Okay, in the 11th in the 10th week, what we have discussed was about type of this clustering method based on type of this clustering method, and that are partitional method, hierarchical method, and hierarchical clustering, partitional clustering, and density based clustering. Okay, and in the last class what we have discussed is regarding another type of clustering called soft clustering, that is Gaussian mixture models. Okay, now this week we will be shifting from this unsupervised learning to reinforcement learning. Okay, now before reinforcement learning we have a theory called this. Okay, someone is joining. Yeah. So before moving into the reinforcement learning, what is important is to discuss with you is a thing called learning theory, that is very important in machine learning. Okay, so before that, what is the science of machine learning research? So machine learning research, if we talk about this machine learning research, it is a mix of mathematical science as well as experimental science. Okay, both mathematical as well as experimental science. Whenever we are talking about mathematical things, that consist of theorems and proofs. Okay, and whenever we are talking about experimental, it is we are putting that machine learning model in a real data for a real data from any experiments. Okay, so that is experimental. So machine learning is a mix of this, both this mathematical as well as experimental science. Now it cannot be alone mathematical or alone experimental. Okay, if it is alone mathematical, what is the problem is alone mathematical, whenever we are proving it by some theorems and proof, we are taking some assumption. Okay, so and we don't know that if that assumption will work in a true experiment field or not. In the other way round, if I talk about experimental, machine learning is fully experimental. That also we cannot say, because we are only applying our machine learning model to our true data. But if we give another data to it, it may behave differently. So experimental also we cannot fully tell it is an experimental thing. So truly it is a strongest contributions will come if we combine both the style of science, that is mathematical as well as experimental. Okay, okay, someone is joining. So yeah, so now about this machine learning theory. What is this machine learning theory? Machine learning theory, it is also known as computational learning theory. Okay, it aims to understand the fundamental principle of learning as a computational process and combines tools from both computer science and statistics. Whenever we are talking about computer science, we are talking about this mathematical part, and whenever we are talking about statistics, we are talking about this experimental part. Okay, so statistics is what, if we are assuming a hypothesis and then we are testing it on a data set. Okay, and then we are proving if that hypothesis is right or wrong. So that is statistics. So statistics is a type of experimental science, whereas if I talk about computer science, it is purely mathematical. Okay, so this machine learning theory is also known as this computational learning theory. It aims to understand the fundamental principle of learning as a computational process. Okay, and it combines both our knowledge from experimental field as well as mathematical field, that is from computer science as well as statistics. Okay, now questions that we can ask from this learning theory. First is, under what assumption can we guarantee some behavior, okay, some behavior of some learning algorithm. Okay, so that is important. Like, what are the assumption that we are uh, under what assumption we can guarantee that some behavior of the machine learning algorithm will always turn true. So that is the first question which is important. Second is, what is the computational complexity of some algorithm? That is again an important thing. Computational complexity means, if I am giving n data points, then what is the time our machine learning model will take to learn throughout the data or throughout the training data. So that is computational complexity. That is, what is the sample complexity required to fit the model. Now it is fully about our training data set. How much should we keep our training data set, and how much complex it should be, such that such that our model fits well. Okay, like you know that two data points cannot be used to make a model. For making a model, we require at least three data points. Like any statistics you can any thing you can tell, like if I give you only two data points, so that is not enough to fully fit our model. We require at least three data points to fully fit our model. Okay, so that is sample complexity, how much complexity we require to fit the model. Fourth is, how many mistakes will an online learner make. Means, if we are continuously learning our algorithm, like some kind of reinforcement learning, like we will discuss later, then how many mistakes will that learner make. And last is, how will a learned model generalize when trained to a finite sample. Because whenever we are giving our data point, that is only a testing training data set. But okay, someone is joining. Yes, so that is only a training data set. But what will happen if we test our model to different data set? How our model will perform? So that is also important. So these are the questions that we require to answer, and this question will be basically answered by our machine learning theory, or also known as computational learning theory. Okay, so is this clear?
Yes, sir.
So today's topic will much more be on theoretical part only, but yeah, definitely there will be some formulas in between. So foundational concept for this theoretical limits of learning algorithm. So there are two foundational concept that is used for this theoretical limit of this machine learning algorithm. First is known as VC dimension. What is this VC dimension? This VC, full form on the scientist name, Vapnik Chernovenkis dimension. It is a dimension which is a measure of capacity or complexity of a hypothesis class. Okay, a set of functions or classifier. Okay, hypothesis class is nothing but a set of function or classifiers. Okay, someone is joining. Okay, so again I am repeating, what is this VC dimension? It is a measure of capacity or complexity of a hypothesis class. It essentially tells us how powerful a learning model is in terms of its ability to classify data correctly. Okay, so this shows that how complex are hypothesis classes. What is a hypothesis class? It is a set of function or classifier, anything you can tell, and it essentially tells us how powerful our learning model is in terms of its ability to classify our data correctly. Okay, means something related to accuracy part, but it is a theoretical science. Okay, it is not a experimental. Whenever we are talking about this metrics called accuracy, precision, etc., these are more related to experimental science. But now we are fully talking about this theoretical science. So VC dimension, it is so it essentially tells you about the capacity or complexity of this hypothesis class. So the VC dimension of a hypothesis H or hypothesis class H is the size of the largest set of points that can be shattered by H. Okay. Now, what is the shattered phenomena? That is important to know what is this VC dimension is. Okay. Okay. So a set of points S is shattered by a hypothesis if for every possible labeling of these points, there exists the hypothesis in H that correctly classifies the points with that labeling. Okay, so if we label our any number of data points, okay, we are talking about binary classification only here, not more than not multi-class classification. We are talking about binary classification only. So in binary classification, if we label our data points in such a way that in such a way that if we label our data points in any possible way, there exists a hypothesis there in H that correctly classify the points with that labeling. Okay, what I am telling, okay, this is the formula of this VC dimension. That is it depends on this definitions only. Okay, so that is the VC dimension is nothing but it is the maximum of points that can be shattered by a hypothesis class. Okay, now example to show you by example, like linear classification in 2D. If we consider a linear classifiers line, okay, linear classifier are nothing but lines only. Okay, so that separates points in 2D plane. The VC dimension of linear classifier in 2D is 3. Okay, so that is the fact that VC dimension of the linear classifier in 2D is 3. This is because 3 points in general position, not collinear. Yeah, we are not talking about it is not collinear. If it is collinear, that it can be separated, but we are talking about these points which are not collinear, that can be shattered by lines, but 4 points cannot always shattered. There are configuration of 4 points that cannot be linearly separated. Okay, so what does this algorithm what does this VC dimension concept tells you is that if VC dimension is nothing but the maximum number of points that can be shattered by a hypothesis H. Okay, so if I take this 2 points in 2D, if I take this 2 points, okay, and what are the possible labels of these 2 points? If I am talking about only binary classification, if I am talking about binary classification, then the classes can be either plus or minus, or it can be A, B, or it can be 0, 1, anything. So we are talking about binary classification. So here I am classifying our points into two labels, plus and minus. Okay, now, okay, someone is joining. Okay, so yeah, here we are yeah, what I'm saying, yeah, if we have 2 points only and we are doing this binary classification, I am giving labeling these points into two classes, one is plus and another one is minus. Okay, now what are the possible labeling of these points can be? It can be plus plus, okay, it can be plus minus, it can be minus plus, and it can be minus minus. Now if I talk about a hypothesis, how I can classify these points, either I can put my hypothesis or put my classifier here. So if I put my classifier here, both the points will be this side, both the positive points will be this side. If I am talking about only positive points, let's say this is positive and this is positive. Okay, if I put my classifier over here, we can easily classify the positive point, and negative point will come over here. Any point in the negative will come over here, but as we are talking about only 2 points, so there are no negative point in this case, only two positive points. So I am putting my classifier over here, and we can separate this positive and negative class. Now what about positive and negative? If there is one positive and the negative, like, okay, okay, so Yeah, like if I tell one positive and another negative, then how I can put my classifier? I can put my classifier right in between. Okay, so right in between, now I can easily shatter this 2 point. So plus minus is also possible. Now again minus plus, if this is not plus but minus, and this is plus, then also we can separate this 2 points. How? By putting a classifier in between. Now minus minus, yeah, minus minus can also be separated. If this is minus, then how I should do, like if I put this minus, and if I put this minus, and if I remove this line, where I have to shift this line, I have to shift this line over here. Okay, so over here, if I put my classifier, this side will be negative only. So by this I can easily classify it. Now what about 3 points? Also, if I work about 3 points also, like plus plus plus, it is shown in the diagram only. Plus plus plus, if you will put it, you can easily shatter your points. Now plus plus minus, if this two are plus and this is minus, then I can put a classifier over here, and I can separate the two sides. Now plus minus plus, if this is plus, this is minus, and this is plus, then again I can put here. Now plus minus minus, like plus minus minus, then also I can put my classifier here. Now minus plus plus, again minus minus of, if it is there, and this is plus, then also I can put my classifier here, and minus minus minus, I can put my classifier here. So 3 points also we can shatter well by our hypothesis. But more than 3 point, if I take a XOR example, like if we have done this XOR example in our perceptron learning algorithm, what we have seen there is, we cannot separate our data points by a straight line. Okay, so if I take this example of the 4 point classification, 4 points with binary classification plus and minus, this labels cannot be separated by a straight line. Okay, you can try it, but this level cannot be separated by a straight line. So the VC dimension of a linear hypothesis is 3. That means it can maximum shatter 3 points only, but whenever we are talking about 4 points, it cannot be shattered. So the VC dimension of a linear classifier is 3. Okay, so is this clear to everyone, what I have told you?
Oh, one question. So instead of 2D, what if it is 3D? Then can it be 4 points, or only 3 points is possible?
3D it should be more than of course 3 points. Okay, you have to check. Also in 3D we do not separate our classifier by line. In 3D we separate it by plane.
Like,
Okay, so there you have to check it. But example of a linear classifier, the VC dimension is 3. Okay, because maximum 3 point can be shattered by a linear machine learning model or linear classifier. Okay. Okay, any doubt in this slide?
so the question will be for 2D alone, or it can be for 3D also, in case they ask.
No, basically we always talk about, whenever we are talking about the shattering concept, we basically explain it by 2D only. But I don't know if the question comes in 3D, but it should not come in 3D, because whenever we are doing that XOR example, there was a question of 3D also, right? In a cube, how we are separating by a plane or not. You remember, I think you can check in my previous slide. Whenever we are doing that XOR example, there was a question of cube also. Okay, so that is 3D, so that can come. Okay, that you can check by your own. But yeah, it can come. I cannot say it cannot come, it can come. But whenever we are explaining, we are always explaining it by two dimension only, because it is easier to process by our mind. Okay.
Okay.
So no doubt, there's no doubt, right, in this slide. What is this VC dimension?
So there is no doubt in this slide, but I have a doubt in one of the previous week's topic. Can I ask that?
Uh, Previous week's topic we can discuss in the next session. There's an extra session on
Okay,
18.
okay, sir.
So
Okay, sir.
what exactly? Which question exactly?
Sir,
Can you
it is
tell?
a numerical. The numerical we got in the assignment, according to me, the answer is something else, but according to them, the answer is something else. The
Actually,
question says,
okay,
okay.
the actually assignment question answer I should not discuss because it is for your evaluation process, right?
No,
So
sir, it
that
has been already, we have already marked it. It is week 11.
okay, okay, I will see. I will see if
Okay.
there is any doubt for
Okay, sir.
okay.
Shall I ask a question or next time I will ask?
Next time you can ask. Also, there is a forum for that. Okay, whenever you are opening, there is a Google group. I think there is a forum for that. That there you can post your queries. Okay,
Okay, sir.
those who are making assignment, they can tell you. Okay, those
Okay, thank you.
yeah, yeah. So that also you can do. There is a Google
Okay.
group. I think there is called a Google forum something. Okay.
Okay, sir.
Oh,
Okay. Thank you.
oh. Now let me move to the next thing called PAC learning. What is this PAC learning? PAC learning defines what it means for a learning algorithm to be successful. Okay, what is the full form of this PAC? PAC means probably approximately correct. Okay, PAC, that means probably approximately correct. So a hypothesis class is PAC learnable if given enough data. The algorithm can produce a hypothesis that is probably with high probability. Okay, approximately correct, that is with a small error margin. So two things are there. What we are doing, we are telling a hypothesis class is PAC learnable if it has got enough training data. So here we are talking about how much training data we want. Okay, so for the algorithm can produce a hypothesis that is probably with high probability. Okay, that is probably approximately correct. That means the hypothesis has hypothesis can be successful with high probability with a small error margin. Okay, so that is PAC learnable. Now what is this PAC learnable formula tells us that a hypothesis class H is PAC learnable if there exists a algorithm that for any distribution of the data can with high probability output a hypothesis H that belongs to capital S such that error of H within a small margin epsilon given a sufficient number of training samples M. The probability is at least 1 minus delta, where delta is a small confidence parameter. So here some things you have to understand is this DVC. This DVC is nothing but your this VC dimension. Okay, DVC is VC dimension. M is the sufficient number of training samples required. That means it is the number of training data required. Epsilon is nothing but it is a small margin. Within this we have to keep our error. Okay, epsilon is that. And there is a delta. Delta is also known as confidence parameter. Okay, someone is joining. Yeah. There is another thing called delta. Delta is a confidence parameter. Okay, so this is the formula of number of training samples that we require. The number of training samples should always be greater than or equal to 1 by epsilon. Epsilon is the error margin that we want to keep our that we want to keep our epsilon is the error margin that we want to keep our hypothesis error margin that we want our hypothesis to be within. And delta is a confidence parameter. Okay, so M should be always greater than or equal to 1 by epsilon DVC. That is this DVC is nothing but your VC dimension of that hypothesis, and log 1 by epsilon plus log 1 by delta. Epsilon is the error margin, delta is your confidence parameter. So this is the formula of the PAC learning. Now, and the important thing that I want to discuss is something called time complexity. Okay, so what is this time complexity? So in theoretical computer science, time complexity is the computational complexity that describes the amount of computer time it takes to run the algorithm. Okay, so simple. We want our algorithm to run. For running the algorithm, how much running, not exactly only running but also learning, okay, the learning process that the algorithm takes. So that is time complexity. Okay, so time complexity can be given by this formula, that is O, K and D. O is nothing but it is a function. Okay, function like we write f here, for time complexity we write this O function. Okay, so K and D. What is this K? K is the number of iterations that you are providing your algorithm to learn again and again. N is the number of data points, and D is the number of features. Like some of the algorithm that extract feature, like any image based algorithm, what it do is it extracts some number of feature. So that is D. So three things are important. One is the number of iteration, on number of iteration that you are giving for your machine learning algorithm to learn. Second is the number of data point, and third is the complexity of the model, which decides the number of features it will extract. Okay, so three things are important to determine this time complexity. Okay, so this is about learning, PAC learning, and time complexity. Okay, what is this PAC learning? P is probably, and AC is approximately correct. So this two things make this PAC learning. Okay, and this is the formula of PAC learning. PAC learning, we use this PAC learning to determine how much the size of a training sample must be, so that the algorithm will be probably approximately correct. Okay, and then there is a term called time complexity. It is nothing but theoretical time that your algorithm will require to learn from that training data, or we can tell in simple words that how much time our algorithm. Okay, someone is joining. Yeah, so how much algorithm how much time our algorithm will take to run this computational model. Okay, so this is about time complexity. Okay, now the another thing is called generalization error. Okay, what is this generalization error? Whatever we are talking about till now is empirical error or empirical risk. Like whatever this VC dimension, PAC learning, whatever they are doing is they are talking about this empirical error. But our true risk, or this true error, true risk, or true risk will be always greater than our empirical risk. Okay, because true risk, whenever we are giving a new set of data, okay, there could be different approximation that for making our model we are using some approximation, but in real world those approximation may not hold. So that is why our true risk will always be true risk will always be lesser than or equal to empirical risk plus this whatever factor. Okay, so this factor is made up of this VC dimension that we have just discussed, and also size of training data, and another thing is called delta. Delta is nothing but here I have mentioned that is the same thing, that is confidence parameter. So with this we can approximate our true risk that will be always greater than our empirical risk. Okay, so this is the thing about true risk and empirical risk. Now if I tell this true risk can be empirical risk if we do not have this terms. Okay, so this term is very important. So to see what is this term, so we can check how we can how our empirical risk and true risk can come close to each other. How it can close to each other? It can be close to each other if we increase our size of the training data, because n is the size of the training data. If we increase the size of keep on increasing the size of our training data, what will happen is this term will become very small. Yeah, there is a n in numerator also, but this n is in log. Okay, so that will be increasing less. But if we keep on increasing n, this n at the denominator will increase, and this will lead to decrease of this term. Okay, so that is why our empirical risk can be very close to our true risk if we keep on increasing our size of the training data. And the one is this is about data. Okay, and the one is about VC dimension. VC dimension, if we keep on increasing the VC dimension, what will happen is our complexity of the model will increase, but that will try our empirical risk and true that will separate the gap between our true risk and empirical risk. Okay, what does that means is, as we keep on increasing the VC, that means our model will be more complex, and whenever our model is more complex, what happens is overfitting increases. That means our model will perform better with our training data, but whenever it comes to testing data, it may not perform well. So that is why, as we keep on increasing the model complexity, our empirical risk and true risk, the gap between our empirical and true risk can enlarge. Okay, so that is the thing about empirical and true risk. Also, there are some graphs over here that is discussed, like yeah, if I take this term as a constant. Okay, so you can say that our true risk and empirical risk gap will be approximately, it is root over 1 by n. So root over 1 by n, you can plot in our plot it, and you can find this graph. Okay, now again, here if I consider all this. Okay, so if I consider this log value also, and if I just eliminate this log delta by 4, that will be very small. So if I eliminate this, then you will get this graph. Okay, now if the complexity is not fixed. Okay, these two cases are if complexity is fixed, that means VC is fixed. Now if VC is not fixed and VC increases with increase in your data set, then what will happen is this term will as we keep on increasing the n, this term will remain constant. Okay, so that is another thing. So these are graphs, there is nothing to be discussed. The important thing is this thing. Okay, this is the true risk, this is the relationship between the true risk and empirical risk. Okay, so this true risk differ from an empirical risk with this factor. Okay, so we have to check that how this factor is depending. So how this factor is depending, this factor depends on mainly two things. One is size of the training data, and second is VC dimension. Size of the training data, it depends on the data you are supplying, and VC dimension, it depends on your algorithm. So these two will determine what is the difference between your true risk and your empirical risk. Now as we keep on increasing the size of the training data, what will happen is this term will remain, this term will keep on decreasing. So our gap between true risk and empirical risk will decrease. But on the other hand, if I tell you, if on the other thing, if I discuss is VC dimension, if we keep on increasing the VC dimension, what will happen is the gap will enlarge. That means the more complex we keep our model, what will happen is it will overfit. How it will overfit? It will overfit because it will perform better in our training data. The more complex our model, it will perform better in our training data, but whenever we will use our testing data, that will not perform better. So this is about generalization error. So any doubt in the generalization error or this time complexity or PAC learning? Any doubt in this? Am I audible?
Yes, sir.
So yeah, so now this is all about learning theory in general. Okay, now we will be moving to the next topic, that is reinforcement learning. Okay, so reinforcement learning, we have talked about supervised learning. We have talked many algorithm of supervised learning. Then we have talked about some clustering algorithms, that is unsupervised learning, and today is the last class that we will discuss about reinforcement learning. Okay, so reinforcement learning is learning about stimuli and action based on rewards and punishment alone. So this is an algorithm that is neither supervised nor unsupervised. Supervised means we are giving both the input as well as output, and let our algorithm learn. Unsupervised means we are only giving input, yeah, and with that input that is not labeled with our input and output, because we are only giving input here, and then we want our algorithm to find certain patterns or something like that. So that is unsupervised learning. But reinforcement learning, whenever we are talking about reinforcement learning, this is neither supervised nor unsupervised. But how it works based on stimuli and action, based on rewards and punishment. So here the agent will perform some action, okay, and the action and the action will be performed on the environment, means the state of the environment will keep on changing. If the state of the environment changes to a positive direction, then the algorithm will give reward to the algorithm. If it changes to a negative direction, that means if the environment does not change good, then it will give a penalty or it will give a punishment. So that is how your agent will learn. Okay, like the example of cycling. Okay, the example of cycling is neither supervised nor unsupervised. Okay, how it is not supervised? Because if it is supervised, then for each if it is supervised, then we are whenever we are learning, we should know that if I pedal this much force, it will move that much distance. So that we do not know, right? Whenever we are learning the cycle, we are just we are how we are learning the cycle. We are learning the cycle with this reward and punishment process only. That means we are just keep on moving our cycle, and we are seeing if we are falling or not. If we are falling, then next time we are trying that we will not do that thing, so that we do not fall. So that is how we learn the cycle. So learning the cycle, or most of the things that happens in our natural world, are nothing but our reinforcement learning, means we are not giving it is not supervised learning. So we are not giving input as well as output. Whenever we are learning the cycle, we are not giving out we are only giving input. We are means we are not labeling the input as well as output, means we do not know that how much force we require so that our cycle will move somewhere, move that distance, or how much angle should we tilt so that we will remain flexible. Nothing like that. We just ride a cycle, and we learn by reward and punishment. If we do not fall, then we give reward to ourselves. That means we will cycle in this way, and if we fall, then we will say that this is a penalty. That means we will not keep on doing that, because we have felt in the previous step. So that is reinforcement learning. So unlike supervised learning, which relies on the training dataset with predefined answer, training dataset with predefined answer, means we are providing both the input as well as output in the supervised learning. But RLs involve the learning through experience. So whenever we are talking about RL, or reinforcement learning, so here we are learning through experience. Now in a RL, an agent learns to achieve a goal in an uncertain, potentially complex environment by performing action and receiving feedback through reward or penalties. So this is a feedback process, means the agent is receiving a feedback. Okay, the feedback in terms of rewards as well as penalties. So if the reinforcement is good, or it is a good enforcement, means it is positively impacting your environment, then your algorithm will give you a reward. Otherwise the algorithm will give you a penalty. So that is about reinforcement learning. Now what are the key concept of reinforcement learning? So one is agent the learner or decision maker, that is the agent. Second is the environment, everything the agent interacts with is known as environment. Third is the state is a specific situation in which the agent find itself. Okay, so state, it can be any part of your learning process. State can be any, you can say any phase of your learning process can be a state, means whenever you are learning, each phase is a state. Fourth is action. All possible moves that the agent make is known as action. So two things are basically important. One is agent, second is action, and this action, how it will impact this environment. Okay, and state is the specific situation in which the agent is. So that is state. And last one is reward. Reward is the feedback from the environment based on the action taken. That is reward. Now if I talk about this, this is the RL framework that I was just discussing. So this is the agent will perform an action, and it will impact the environment. The environment will give environment will give evaluation to the agent, okay, and environment will decide, and after the evaluation process is done, the agent will be in that particular state because action has been performed on the environment. So that is about environment, agent, action, environment, and state. So these are the four things. And this evaluation is nothing but your reward or penalty, whatever that is, evaluation. So these are the five things. So agent is the learner or decision maker. This is the agent. Action, all possible moves that the agent will do, that is the action. Environment is something that the agent interacts with, like when you are learning the cycle, it is the cycle that is the environment cycle, and the cycle which is you are operating in, that is the environment. And evaluation is that reward and penalty. And state is the specific situation the agent is in, so that is state. So these are the five important key concept of our RL framework. Now, how the reinforcement learning works, we have already discussed, but let's discuss in detail. So RL operates on the principle of learning optimal behavior through trial and error. So reinforcement learning is nothing but you are doing trial and error only. Whenever you are learning the cycle, you are doing nothing but trial and error only. You are trying, like, to cycle in a certain way. If it does not force, you are motivating yourself to operate in that way. Otherwise you are changing your plans. So that is nothing but trial and error process, okay, trial and error, that is nothing. So reinforcement learning learns by optimal behavior through this trial and error. The agent takes action within the environment, receives reward or penalty, and adjusts its behavior to maximize the cumulative reward. Okay, so at last, what we require, like in supervised learning algorithm, what we do is we want to minimize our certain things like RSS, that is residual sum of square error, or maximize log likelihood, something like that. Here we are, what our goal is to maximize this cumulative reward. Okay, so that is our goal. If we maximize the cumulative reward, then our algorithm is learning well. So that is how we judge our reinforcement learning algorithm. Now this reinforcement learning algorithm, it has a policy, reward function, value function, and model of the environment. What is the policy? Policy is the strategy used by agent to determine the next action based on the current state. So action is the move that the agent is making, but there is a policy or there is a strategy of the algorithm that based on this state what we will do next. So that is policy. Second is this reward function. Okay, let me pull it up. Yeah, a reward function, a function that provides a scalar feedback signal based on the state and action. So it is nothing but after performing the action, you are after performing the action, you will be on a certain state. So based on that state, how much is the feedback your algorithm is giving you, and this is a scalar feedback because our uh, our algorithm uh, always works with number only. So this is a scalar feedback. Then third is value function, a function that estimates the expected cumulative reward from a given state. That is the value function. Means now we are talking about cumulative reward that we can expect from this algorithm when it is in a given state. Now fourth is the model of the environment, a representation of the environment that helps in planning by predicting future states and rewards. So that is nothing but we are preparing a model such that it is a representation of environment that helps in planning by predicting future states and rewards. Okay, so that is the model of the environment. So these are the four things that is important in the reinforcement learning. So any doubt in this slide? Am I audible?
Yes, sir.
Yeah. So yeah. So now what we will do, we will we will be yeah, we will be taking an example of a reinforcement learning that is very common, that is known as Pavlov's dog's experiment. And this is very a famous experiment. And what is this Pavlov's dog experiment? Pavlov was originally studying the digestive system in dogs, particularly their salivary reflex in response to food. Okay, so that he was studying. So that is why it is known as Pavlov's dog's experiment. So during the experiment, he noticed that dog began to salivate not just when they were presented with food, but also when they saw lab assistant who feed them, or even when they heard sound of footstep. So this observation led Pavlov to explore how behavior could be learned through this association. So there are some key elements of this. Okay. Yeah. Again, I am repeating what was this Pavlov's dog experiment. So originally he was studying the digestive system in dogs. Particularly, he was watching that how the dog's salivary reflex was in response to the food given to the dog. Okay, but during the experiment, what he noticed was that the dog began to salivate even when he was not presented with food. But when the dog saw the lab assistant who feed them, or even when he saw the heard the sound of the footstep, because he was assuming that someone was coming to give him to feed him. So that is how this observation led Pavlov to explore how behaviors could be learned through association. Means even if the food is not provided to the dog, how his behavior is changing. So there are some key elements to this Pavlov's dogs experiment. One is unconditional stimulus. So what is this unconditional stimulus, or also known as UCS? This is a stimulus that naturally and automatically triggers a response without any prior learning. In uh, in Pavlov in Pavlov's experiment, the food was unconditional stimulus because it naturally caused the dog to salivate. So, what is this unconditional stimulus? This is a stimulus that naturally and automatically triggers a response without prior learning. Like whenever you will give food to a dog, he will salivate. So there is no learning thing here. Okay, that is natural. So that is why this type of stimulus is known as unconditional stimulus. And there is a unconditional response. What is this unconditional response? This is the automatic natural reaction to the unconditional stimulus. Like in this case, whenever the dog is given food, this salivation is a unconditional response. So two things: one is unconditional stimulus, second is unconditional response. So unconditional stimulus is what? Food. But unconditional response is what? That is nothing but salivation. So these are the two things. That is, we do not require any learning process. That means it is natural thing. But then there are some conditional stimulus also. So before conditional stimulus, there is a term called neutral stimulus. Okay, what is this neutral stimulus? This is a stimulus that initially does not trigger any significant response. Like in Pavlov's experiment, the sound of a bell or tuning fork was used as a neutral stimulus. Means when initially there was no trigger with this sound of bell or tuning fork. So that is why this is neutral stimulus. But what is this conditional stimulus? After neutral stimulus is repeatedly paired with this unconditional stimulus, that means now with this neutral stimulus, that is sound of bell or this tuning for sound of bell or tuning fork, when it is paired with this food, means when we are giving the dog food, as well as when we are combining this with sound of bell or any tuning fork. What happens is, repeatedly when we do it, it becomes a unconditional, the neutral stimulus will become a unconditional stimulus. That is, it becomes a conditional stimulus. That means, after this training, what will happen is, even if the dog does not even if the dog does not see the food, but it only heard the sound of the bell, then also his unconditional response will come. Then also he will salivate. So that is why this is known as conditional stimulus. So this neutral stimulus will only become conditional stimulus when we pair this neutral stimulus with unconditional stimulus. So unconditional stimulus plus neutral stimulus will be equal to this conditional stimulus after we do this repeatedly. That means we do this through a learning process. So uh, so now, another thing is conditional response. In this case, when we do this conditional stimulus, that will be salivation only. So that is conditional response to this stimulus. So basically there are two important things. One is known as stimulus, and the one is known as response. So the stimulus can be unconditional, neutral, as well as conditional. What is this unconditional stimulus? That is natural stimulus, means whenever you are giving food to a dog, he will salivate. So this food is a unconditional stimulus. Now what is this neutral stimulus? Neutral stimulus means like sound of a tuning fork or sound of a bell. Whenever you will do the sound of a bell or sound of a tuning fork, initially the dog will not salivate. Okay, but when this neutral stimulus is combined with this unconditional stimulus, what will happen is the mind of the dog will be trained. So after that, what will happen is, even if you will give only a neutral stimulus, this neutral stimulus will now be called as a conditioned stimulus, because the brain of the dog is already trained. Now whenever you are giving it a conditional stimulus, that is nothing but only neutral stimulus. In this step, what will happen is the dog will salivate. So these are the important concept about Pavlov's dog experiment. Okay, now this is the process you can see. First, before conditioning, what will happen is, whenever you are giving food, the dog will salivate. So that is natural response. And whenever you are giving bell, the dog will not salivate, so no response. So this is neutral stimulus, doesn't cause salivation. But during conditioning, what you will pair this conditional as well as unconditional stimulus. That is, you will also ring the bell at a time, also you will give food at a time. So simultaneously you will give food as well as ring the bell. So the conditioning or the learning of the dog's brain will take place. Okay, and after conditioning, what will happen is, even if you are providing if you are only updating the whenever you are only ringing the bell, it will lead to salivation, because the dog mind has already been conditioned. So this is about Pavlov dog experiment. So is it clear to everyone? This is very important experiment. Why it is important experiment is, even this Pavlov dog experiment, the concept of the Pavlov dog experiment is still now being used. Like whatever ad you are seeing, there are some you can see that in some of the ads or advertisements, so you will see you will be hearing some song that you already know. So what will happen is, you only like that song, but due to that song you will like that advertisement also, and you will keep buying the product. So that is how Pavlov dog experiment still influences us in many things. Like also phobia, if you note something called phobia, like we are some are phobic to height, or some are phobic to certain things. So that is also some kind of this conditioning and unconditioning, this conditioning process only. So before you can say that before some bad incident happened, like a person is phobic to altitude. So before by birth he will not be phobic to altitude, but what happened is he might have gone to some place, and some bad incident he might have seen some incident happening, or some bad incident might have happened with him, and after that he will be phobic to altitude. So this Pavlov dog experiment is very important. Okay, so is this clear to all of you? What are the responses? What are the stimulus? Any doubt in this?
So that conditional stimulus and all those things, those can be generalized or what?
Yeah, it can be generalized. I have told you, right? Like advertisement, till now advertisement process use this conditional use this learning. Okay, conditional learning. How it use? It will be playing some of the music that you already like there is a old song that you might have liked, and then this advertisement will play those song only. So what will happen is you actually like the song at the first place, but now as this that if this ad has been played without the song, you might not like this product as much, but as the song is being played in the background, you would like that product much. So this thing is still being used, okay, in different things, okay.
Okay.
Okay. So is this clear? What is this stimulus? What is a response? Is this two terms clear? This is very important in our reinforcement learning. Okay. No doubt regarding this, right? Okay. Now we will be learning one of the algorithm called qlearning. Okay, so the qlearning is a reinforcement learning algorithm used to find the optimal action selection policy for a given environment. It is used in an environment where an agent learns to maximize the cumulative reward by interacting with the environment over time. So the agent learns a policy to decide whether the action to take in each state of the environment to achieve the highest reward. So this is definition of nothing but this reinforcement learning only. So this Q learning is an algorithm of reinforcement learning only. So this key concept of reinforcement learning: agent you already know, environment you already know, state you already know, action you also know, reward I have told, policy you know. Now there is a thing called value function. Value function is also, I have told you, that is expected long term reward the agent will get starting from a particular state. Okay, so that is the cumulative thing that I was talking about. And for this q learning process, there is a key concept called q value, or action value. So what is this q value? Q value, it represents the expected cumulative reward of the of taking an action in a state S and following the optimal policy thereafter. So it both combines your action, state as well as policy, and it represents the expected cumulative reward that you will get from thereafter. So Q value are used to determine the quality of an action taken from a given state. So there are three things that is important. One is state, second one is action, third one is policy. So this Q value, what it do is it represents the expected cumulative reward of taking action in a state and following the optimal policy thereafter. So how much reward you will expect, the how much cumulative reward you will expect. So that is the Q value decide. So that is why this algorithm is known as Q learning, because we are representing the expected cumulative award by a value called Q value, or also known as action value. So what is represent? It represents the expected cumulative reward of taking an action in a status and following the optimal policy thereafter. So this is the qlearning algorithm. You can see this is the updated q value. This is the original q value, but updated q value will be equal to your updated q value will be equal to your original q value plus alpha. Alpha is nothing but the learning rate. Learning rate controls how much the new information override the old information. A higher value of alpha means the agent learn faster. Okay. Now this is about learning rate. Second one is R. R, you can see in the formula R. What is this R? R, the immediate reward received after taking an action A instead S. That is R. Now what is this gamma? Gamma is the discount factor. It represents the agent value how much agent values future reward. A higher gamma means future rewards are given more weight. Okay, higher gamma means future rewards are given much weight. So this is something regarding to that weight process. Means if the reward is good, then you are giving more weight to the reward. So that is known as discount factor.
So
Now there is
future
a
reward,
yeah.
this future reward is the immediate next step, or all the next steps are included in this?
No, immediate step. We are talking about immediate step, because by immediate step only we are updating the q value. Okay,
Okay. Okay.
this is the previous q value and this is the new q value. Okay, how our previous q value is updated? Previous q value is updated by adding this. So what is this? Alpha is our learning parameter, R is the reward, gamma is the discount factor. Now this maximum this thing maximize with respect to a dash. A dash is your yeah, s dash a dash. So s dash a dash is your q value of the next state. So maximum q value for next state s dash across all possible action a dash. Okay, this represents the agent's estimate of best future reward from state s dash. S dash, the next state resulting from the action A in state S. Now F shallow, there is another two terms called F shallow and N episode. So F shallow, the exploration rate in reinforcement learning determine the probability of taking a random action to explore versus exploiting the best known action. So any algorithm, there are two things. One is one is exploration, and second is exploitation. So first, whenever we are searching, like whenever you are searching a coin in a large room, whatever, first what you are doing is you are exploring the room, and then wherever you are thinking that there is a more possibility of that coin being at that room on that place only, then there you are doing exploitation. So two things are important. One is exploration and second is exploitation. So what is this epsilon? This epsilon the exploration rate in a reinforcement learning, it determines the probability of taking a random action to explore versus exploiting the best known action. Okay, and last is an episode. This is nothing but your number of iteration, you can say. So the number of complete learning trials or number of iteration, you can say, iteration or interactions the agent perform with the environment to learn the optimal behavior. That means how much time you are making the model learn. So that is an episodes. Okay. With this we can use this qlearning algorithm. We can use this qlearning algorithm to use see our this Pavlov's dogs experiment. How we will do this? First we will be importing our libraries. So these are the libraries that is required here. We do not require any hi-fi libraries here. These are the libraries that is required, and NumPy and Matplotlib, because reinforcement learning there are no important libraries. So this by this two library only we can run our code. So one is NumPy. Why we require NumPy? NumPy, we are requiring NumPy to process our data. Okay, and second we require Matplotlib to plot our results. So these are the two libraries required. And now we will define the environment. How we will define the environment? we will define the environment by this states. Okay, so there are four state, 0 1 2 3 0 1 2 3. There are four steps. First state is no bell, no food. Second state is bell and no food. Third state is bell and food. And fourth state is no bell and food. So reward, what will be a reward? Reward, the dog receives a positive reward when it expects a food after the bell. Okay, that is state 2. That means whenever after state 2 only, uh, uh, after state 2 only, that is this one state. Okay, because this is the first state, this is second, this is third, this is fourth state. So the state that is indexed 1, so after this state only we can expect a positive reward, because after this state only there is food and there is food. So salivation will take place when there is food, before learning, and after learning salivation will take place when there is bell. So this state, this zero state will not yield reward at any position, because whenever we are going for this zero state, that means no bell or no food, the dog will not salivate. So that is why there will be no reward in this first state, but there will be reward from state second, third and fourth. The state second, state third and fourth will receive reward even when it is not trained, but state first will receive award when the learning process will get completed. Okay, so this is how now we are putting this reward into a numpy array, because we can process our data with this numpy array only. So how we are processing our data? We have 4 rows and we have 4 columns. So what is this rows and columns? See, this rows defines state. Okay, state 0, this first row means state 0, this second row means state 1, this third row means state 2, and this fourth row is state 3. So these are the 4 state we have. Now what are these columns? These columns are nothing but your reward after an action. Okay, so after an action that is happening in this state, we are getting a reward. Okay, so how we are getting a reward at the third position? How we are getting a reward after third position? Because after our second state only we are ringing the bell, so that is why 10 here. Now again here whenever we are ringing the bell, whenever we are giving food, the dog will salivate, so that is why 10 is here. Now no bell but food, again it will be moving backwards, so that is why 10 we are applying here. So this can be appear confusing, but let me again tell you, this 4 rows means 4 state. Okay, these are the 4 state that we are providing the dog. First is no bell no food, second is bell no food, third is bell food, and last one is no bell and food. Okay, now there are action that will provide us a reward. This is 1 1, that means this we are talking about state 0 only. So state 0 in all the position we are giving, we are not giving any reward, because state 0 means no bell as well as no food. So 0 in all the position, but here we are giving 10 at the third position, because after second state only the dog will salivate, so that is why 10 here. Now here also 10, because after bell the dog will salivate, and here also 10 means no bell but food is there, so it will be this step only, because even if no bell, so food, the dog is receiving food, so that is why 10 is written here only. So that is how we have conditioned our numpy, processed our numpy array. Now
So,
what we
but in
will,
that, what is the second state in that particular array? Like square. Uh,
yeah,
so why
this is,
is it like still in second state? Why we are setting? I mean, in the second row, third column. Why we are setting the 10?
yeah, because see, this is this rows are nothing but your state, and this is nothing but rewards after an action. Okay, so when the dog will salivate, the dog will only salivate after this first stage, that is after the learning process will get complete. What will do, the dog will salivate after even if there is no food and only bell is rang, the dog will salivate. So that is why 10 over here. Now here also bell and food is there, so then also the same reward will be given to the state also, so that is why 10. And here no bell no food, so again no bell and food, so as the dog is receiving food, so that is why we are giving 10 here. Okay.
But before conditioning, the dog will not salivate before the
Yeah,
on bell and no food, right? So
yeah, but still we have to keep our rewards like this, then only our algorithm will learn. Okay, so that is why
okay,
we have to keep the reward here only. Okay.
okay.
Now here we are number of state and action, so whatever the state and actions are there, so we are just writing it, so that our yeah state and action 0 and 1. 0 means 0 means this row and 1 means column, so that is why, that is what this n state means. These are the rows means states, and action after an action, so an action means the rewards will be supplied after each action. So one means this columns, at columns you will be applying the rewards. So that is what has been coded here. And now we are initializing the Q table. How we initialize our Q table? We initialize our Q table with this states and action only. So by this we are initializing our Q table. Now we have this hyperparameters, okay, alpha, gamma, epsilon, and episodes. So these are hyperparameters. Hyperparameters are nothing but parameters used in our training process. Okay. So I have already discussed the learning rate, gamma discount factor, exploration rate, and an episode is nothing but number of iterations. Now cumulative reward, we are tracking the cumulative reward, so that is why we are applying a null set. So in this set, the cumulative reward will count. Now this is the qlearning algorithm. You can check, these are the steps. First is choose action using epsilon greedy strategy, so this you can check. I am giving you the code, this you can check. So after this learning process, these are the results that you can see. So after this learning process, what you will see, with the number of episodes, the density of your cumulative reward will increase. Like here the density is less, but as you keep on moving here, the density of the cumulative rewards will increase. So that means our algorithm is learning. So that is how we are checking this. Checking this with plotting the episode or number of iteration with cumulative reward. So as we keep on increasing the number of episode, our cumulative reward, the density of cumulative reward will increase. That means our algorithm is learning well. So by this we are evaluating. This is one process of visualizing the evaluation process. Now another thing is visualizing the Q table. So Q table is made up of two things. One is action and another one is states. So this is the Q table, and in Q table you can see uh, this is nothing but this is known as heat map. Okay, so heat map is from 0 to 10. This 0 means this blue color means 0 and this red color means 10. Okay, and in between color you can see. So you can in this you can properly see that this is known as action, means x-axis this is action and y-axis is the state. So at 2 comma 1, that means at when there is bell and food, and your state is 1, that means 1 means bell and no food, means whenever you are now you have made your algorithm learned in such a way that that this action, that bell and food has been conditioned in such a way that this action will lead to this state, that is bell and no food. That means your algorithm has learned that whenever there will be a action called bell and food, at this action your algorithm will be automatically in this state. That means your algorithm will tell that it is no bell and food. Okay, sorry, bell and no food. So that is how your algorithm has learned that. So the q table here, you can see the heat map for 2 comma 1, that is action 2, and state 1, that is maximum, reward, that is 10 is given to this state. Okay, that means the at this whenever the action was bell and food, your algorithm has learned that the state will be sorry, you can understand in this way also, that whenever your state was bell and no food, your algorithm has learned that is bell and food. So that is why this action, the algorithm will be taking this action. So that is how your algorithm has learned that. So this q table you can analyze, and this is the final q table after printing. Okay, this is same as this, but only this numbers are written all same as this. You can see at this state this 10 is given, that means this is nothing but your state 2 or state 0, state 1, and this is your action third, action 2 means action 0 1 2. So at this position only you are achieving the maximum reward. So by this you can code your Pavlov dog experiment. So any doubt in this? You can after this class you can download this code and you can properly see it how we have coded it. Okay.
Can you show the code?
Yeah,
The
yeah.
proof, I mean, can you scroll down? Can you show that?
Is it scrolled or it is not scrolled?
Yeah, no, not. We are at qlearning algorithm.
Okay, okay, okay. So this is the algorithm. Okay,
Okay, okay.
this is the algorithm. How we are choosing the action, and then stimulating the environment, then updating the q value. This is the algorithm. This full is the algorithm. Okay, you can check it. This is the qlearning algorithm. I have properly texted it. So texted it by a comment, so you can properly see it. Okay, this you can download and you can see how we have coded this Pavlov dog experiment. But what apart from coding, this Pavlov dog experiment is you should understand this Pavlov dog experiment. This is one of the basic experiment that explains the reinforcement learning, and also this has been used till now again and again. So this is very important. So I hope you all understand what is this Pavlov dog experiment. So that is the most important thing. So any doubt in this Pavlov dog experiment? No doubt, right?
No doubt.
Sir,
Yeah, please.
sir, please share your notes as well, handwritten notes as well, if possible, for the course.
Handwritten notes, I don't have any handwritten notes. I put everything in the slide, so you can download the slides. Okay,
Okay, okay.
you can download. You all know, right, where the slides are available, or don't know it? Whenever
Yes,
yeah,
we
whenever
know.
you whenever you are opening the swam portal, wherever the week 1, week 2, etc are there, at below there will be something called problem solving session or something like that, or live session, something like that. Whenever you will open that problem solving session, there will be a Google sheet coming. In the Google sheet there are 3 TAs, because there are 3 TA assigned for this course. In the middle one you will find my content. In that table you will find week wise the YouTube recording that is provided to you, that is provided that is we have discussed in the class, all the week 1 to week 12. And there will be in the middle column there will be something called presentation folder. Whenever you will open the presentation folder, there will be all the presentation that I have shared with you. Also in that presentation folder I have keep all the codes, what we have discussed as well as what we have not discussed, all the codes, all the algorithm that we have discussed. I have prepared the codes for all the algorithm and I have put in that folder. Okay, and also there are, I think I have kept two books for you. One is for elements of statistical learning, and another one is I think pattern recognition and machine learning. So that two books also you can use it for your reference purpose. Okay, clear, right?
Yes, sir.
No doubt regarding where is the content available, right? Because this is very important, because otherwise if you don't know where the content is available, you won't find this codes also. So that is why I have told this again. Is my slides clear to all of you?
Yes, sir.
Yeah. So now we will be moving to our question answer session. So question answer, I request everyone to guess the answer first, and then we will discuss it. Okay. So okay. So this is the first question.
D, sir.
Yeah,
D, sir.
yeah. Someone is telling D. Okay. So let me read it. Statement one. Empirical error is always greater than generalization error. Okay. Second is training data and test data have different underlying true distribution. Choose the correct option. Okay. Training and test data have different underlying true distribution. So you are telling D. So yeah, D is the correct answer. So first is empirical error is always greater than generalization error. So no, empirical error is always less than your true error or generalization error, because true error will be taking in consideration the other factors also, but your empirical error will always consider the theory behind it only, and not the experimental thing. For the experimental thing, we for accommodating the experimental thing, we have a separate we have a factor. So by adding that factor, our this empirical error will reach the generalization error. So first statement is wrong. Now second is training data and test data have different underlying distribution. So in fact it is typically less than generalization error, since the model tends to perform better. Now training data and test data have different underlying true distributions. So that is not the case, because training data and test data, it will be applying the same algorithm. Also it will have same distribution, because training data and test data, we are dividing our data into two sets or three sets. So in machine learning generally we use two sets, that is training and testing. So training data and testing data will be coming from the same distribution. Also the same algorithm will be applied to the training as well as testing data. So that is why statement second is also false. So so option D is the correct answer, that is both are false. Okay. So statement so both are false. So option D is the correct answer. Now moving on to the next question. Let probability of AI equals to 2 to the power minus I. Calculate the upper bound, that is probability union I equals to 1 to 5 AI using union bound around to 3 decimal places. So how we will solve this? We know that if we whenever we are doing intersection of different sets, what will happen is, whenever we are doing union of different set, what will happen is, it can be it can have common values, or it can have common intersection. Okay, so that is why our probability of this whole probability of the whole set, that is A1 union A2 union A3 union A4 union A5, will be always lesser than or equal to when we are taking it separately. That is probability of A1 plus probability of A2 plus probability of A3, A4 and A5. So here we have been asked what is the union bound. Okay, union bounds means what is the upper bound of it. So upper bound, how we can calculate it? We can calculate it by replacing the greater than equal to sign by with equal to sign. That means this P A1, A2, A3, A4 and A5 will be equal to P A1, A2, A3, A4 and A5. Okay, so that will be equal to A1 for A1, A1 will be equal to 2 to the power minus 1. Okay, A2 will be equal to 2 to the power minus 2. Okay, A3 will be equal to 2 to the power minus 3, like that. A4, A5 and A4 and A5. Okay, so you will 2 to the power minus 1 is 1 by 2. Okay, 1 by 2 plus this is 1 by 2, then this is 1 by 4 plus this is 1 by 8 plus this is 1 by 16 and last one is 1 by 32. Okay, you will take the LCM. What is the LCM? The LCM will be 32. This will be 16 plus 4 8. This will be 8. 16 plus 8 plus 4 plus 2 plus 1. So that will be equal to 24, 28, 24, 28, 30 and 31. That will be equal to 31 by 32. And 31 by 32 will be equal to this 0.96875, and we have to round it to 3 decimal place, so that is why 0.969. So option C will be your correct answer. Okay, so you got this right, how we get this formula? Because whenever we are doing the union process, there will be some data points that can be common in two sets. So that is why whenever we are doing union, that will be equal to individual probabilities only if there is no intersection. Otherwise it will be lesser than our it will be lesser than our individual probability sum. Okay, so the maximum bound or the union bound will be equal to when there is no intersection of all the sets. So whenever there will be no intersection of all the sets, your probability A1 union A2 union A3 union A4 union A5 will be equal to, whenever there will be no intersection, it will be only equal to, not less than. Okay, it will be always equal to less than if there is intersection. If there is no intersection, then it will be equal to okay, that will be equal to. So that will be equal to, and that will give you this maximum bound, and you will calculate this by this, because PAI is already given 2 to the power minus I. So PA1 will be equal to 1 by 2, PA2 will be equal to 1 by 2 square, that is 1 by 4, PA3 will be equal to 1 by 2 cube, that is 1 by 8, PA4 will be equal to 1 by 16, and PA5 will be equal to 1 by 2 to the power 5, that is 1 by 32. You will solve it and your answer will come 31 by 32, that will be equal to 0.96875, and when we will approximate it to 3 decimal place, that will be equal to 0.969. So option C is your correct answer. Is it clear?
Sir, suppose if it is a lower bound means it is equal to probability, sir.
Yeah, if it is equal to lower bound, then we cannot calculate it. That will be equal lesser than, okay, lesser than something, P1 plus P2 P3, that we cannot
Upper
calculate.
bound, lower bound, both for less than only, sir.
Both for less than, no, less than equal to, this is the formula. Okay, upper bound
Yes,
will be when it will be equal to. Okay, and lower bound we don't know. Lower bound means the intersection will be as much. Whenever the intersection will be more, then it will be lower bound, right?
sir. Okay.
Now, question number 3, statement A, reinforcement learning is a type of unsupervised learning. Statement B, reinforcement learning does not have labels. So,
Sir, both are
option
false, sir.
both are
D.
False.
D. Both are false. Someone is telling both are false, someone is telling D. Yeah, so let me read it. Reinforcement learning is a type of unsupervised learning. So this is false, right? This is false because reinforcement learning is a third type of learning, that is neither supervised nor unsupervised. We cannot compare it by supervised learning because we are not providing any label. So reinforcement learning does not have any labels. Okay, so reinforcement learning does not have any label. So this is a true statement, right? So option statement A is wrong, but statement B is right because it does not have any label. So that is right. Okay, so statement A is false, statement B is true. So option D is the correct answer. Okay, because supervised learning, it is input, output as well as labels. Input, expected output and labels. Also, whenever we are training the supervised learning, we are providing input as well as output. Okay, this output is nothing but your labels only, right? And this reinforcement learning, we have input, that is the current position, that is also known as state, and we have an expected action. We do not have labels in reinforcement learning. So option D is the correct answer. Okay.
Sir, suppose the given learning is supervised means we have a label, right, sir, for the given inputs.
Yeah, yeah, yeah.
But how come labels are not in referring according to that supervised, the inputs and labels will be there. But in
Can
the
you please
statement,
repeat?
sir, in the supervised learning, the
Yeah,
labels will be there for the given inputs.
yeah. Supervised label will be there.
Yeah,
Yes, yes.
yeah, yeah. But according to the statement B, reinforcement learning does not have a labels.
Yeah,
Suppose if it is supervised means the labels should be there, no, sir?
reinforcement learning is not supervised learning, right? Reinforcement learning is the third type of learning, right? Not supervised. So it does not have label, right? Like cycling. Okay, cycling cannot be supervised learning, because if it is supervised, then whenever you are learning the cycle, you should know that how much force I will apply and how much the cycle will move forward. But that you don't know, right? Whenever you are learning cycle, you are just applying some kind of force, and it moves some distance forward. So it is not labeled. But if it is labeled, then you should know that I am putting 5 pound force, and my cycle will move to that as my cycle will move forward by that much meter or that much foot. So that is supervised learning. But whenever you are learning a cycle, that is unsupervised learning, because whenever you are learning, you don't know that how much force your cycle will move, how much distance. But you are learning it by trial and error only. Means you are learning it, you are first applying some force, you are seeing how much your cycle is moving, and then if it is not moving forward much, then you are applying more force, like that. So that is why learning cycle is a cycle is a reinforcement learning and not a supervised learning. Okay, so supervised learning only will have label, not unsupervised learning also do not have label. Reinforcement learning does not have label. So only supervised learning have labels. Okay.
So then reinforcement is a supervised learning, no, sir?
Reinforcement is not a supervised
Not
learning,
a
right?
supervised.
Yeah, reinforcement learning is the third type of learning. It is neither
Oh,
supervised nor unsupervised. Okay,
okay, sir.
I hope this is clear.
Yes, sir.
Okay. Now let me move on to the next question. If a hypothesis class has a VC dimension of 4, what does it imply? It can shatter any set of 4 points but not any set of 5 points. It can perfectly classify any dataset. It will always have zero training error. It requires at least 4 training samples to achieve a low generalization error. So any guesses for this?
Yes, sir.
D,
Yeah,
sir. D, sir.
D.
Yes, sir.
Yeah, A.
Three means four, more than three or four.
Yeah. So A is correct. So is anyone telling D? D is not correct. Okay. A is correct answer. So VC dimension of 4 means hypothesis can shatter any set of 4 points, but we do not have guarantee that it will shatter 5 point or not. Okay, it will not able to shatter 5 point. So that is the thing. So option A is the correct answer. Okay, it requires least 4 training sample. Whenever we are talking about training samples, so this is nothing but PAC thing. Okay, not your VC dimension thing. So this is a false statement. Okay. VC dimension means we are only talking about how our algorithm is shattering, will able to shatter points or not. VC dimension is related more to our algorithm, but whenever we are talking about PAC, it also gives some knowledge about what should be our training data sample, how much should be our training points in our data sample. So option A is the correct answer. Okay, I hope this is clear to all of you. Now let me move on to the next question. What is the VC dimension of all set of linear classifier in 2D? This is again a very important question. That is why it has been put.
Three,
So,
sir.
uh, what? B or C?
Three. Three.
Yeah,
C.
C. Yeah, C.
Three, sir.
Yeah, C. Yeah, absolutely right. The VC dimension of the set of all linear classifier in 2D classifier is 3 that we have already discussed. Like here we have discussed in detail. Okay, you can see this. You can see this 3 graphs and you can understand. After these 3 points, whenever we are taking the 4 point, it cannot be shattered by a 2D linear classifier. This is an example of XOR. Okay, we have discussed in our perceptron learning algorithm. So our perceptron learning algorithm don't function when we have perceptron learning algorithm also don't function when our data set cannot be linearly separable. Okay, so this is again related to that only. Okay, so 4 points cannot be shattered by a 2D linear classifier. That is why 2D linear classifier VC dimension is 3. Okay, so option C is the correct answer. Okay, now let me move on to the next question. What is the policy in reinforcement learning? First option A is a mapping from state to action. Option B, a mapping from states to rewards. Option C, a mapping from actions to rewards. And option D, a mapping from action to next state. So any guesses for this?
Sir, B. States to reward.
States to rewards. Okay, so policy in reinforcement learning is nothing but a mapping from states to action. Okay, states to action, because we are mapping from state to an action. Okay, that is the policy. Okay, so that is why not states to reward but states to action. Reward is a feedback process. Okay, that comes after our action has been taken place by that policy. Okay, so option A is the correct statement. Okay, so let me move to this. This is an interesting question. Alien challenge you to a complex game that no human has seen before. They give you time to learn the game and develop strategies before a final showdown. Okay, you choose to use a machine learning because an intelligent machine is your only hope. Which machine learning paradigm should you choose for this? Option A, supervised learning. Option B, unsupervised learning. Option C, reinforcement learning. Option D, use a random number generator and hope
C.
for the best. Yeah, C. C is the correct answer. Okay, supervised learning you cannot use it because like learning a cycle is a complex process, that this is also a complex game. So you don't know the output beforehand. Okay, so unsupervised learning is of course of no use, because unsupervised learning we are learning patterns or like that. So that is also no use. Reinforcement learning we can use because reinforcement learning always learn by the process of this penalties and rewards and penalties. So our machine will learn by this reinforcement learning. Okay, reinforcement learning is the optimal for building agent for complex game where no trajectories exist. That means whenever there is no labeled dataset beforehand, that means we do not know that by this action what will happen. So for that we always prefer this reinforcement learning over supervised learning. Okay, if we have labeled dataset before our hand, that means if we know beforehand that how with each step how with each step how we can learn, then we can use supervised learning. But we do not know beforehand that which each step how we will win the game, or how we will progress the game, then we will use this reinforcement learning. Supervised learning has more accuracy than reinforcement learning, but supervised learning will fail here because we do not have a labeled data set before. That means we beforehand we do not know what is the output for our certain input. So that is why we will be using our reinforcement learning. So option C is the correct answer. Okay. So I hope this question is clear to all of you, why we are not using supervised learning and why we are using reinforcement learning. Okay.
Yes.
Okay, so let me move on to the next question. So you want to create a self-driving car software in the context of the standard reinforcement learning framework. What would you classify as the state and action? Note that your system does not have access to previous state. So what will be state and action? Option A, state will be your current steering wheel position and the current pedal position and current speed. Action will be turn the steering wheel, press the pedal. Option B, current state will be current steering wheel position and current pedal position and current acceleration. Action will be turn the steering wheel, press the pedal. Option C, current wheel position is a state will be current steering wheel position, current pedal position and current speed, and action will be current change direction and change speed. And option D will be current state will be current steering wheel position, current pedal position, current acceleration. Action is change direction, change speed. So any guesses for this?
Sir,
Self,
A.
yeah,
A.
A,
A,
B,
sir.
yeah, A, B, okay. Okay, so let's see the answer. So answer is option A, that is your current state will be state will be current steering wheel position, current pedal position and current speed that you can see with your naked eye. Current speed will be shown by your speedometer, current pedal position you can see, and current steering wheel position also you can see. And what will be your action? Your action will be turn the steering wheel by for changing direction. What we will do, you will turn the steering wheel, and for speeding up your vehicle, what we will do, you will press the pedal. Okay, so these are the two things you can do. So these are the actions you can perform. So option A is your option A is your correct answer. Okay. Current acceleration cannot be seen, so that is why this is false. Here current speed, current pedal position, change direction, change speed. So change direction, change speed you cannot do, but you can rather turn the steering wheel, press the pedal. So that is why this is false, because this action does not fully determine your self-driving car. That is change direction and change speed that you cannot tell your algorithm. You have to tell the algorithm, you have to turn the steering wheel or you have to press the pedal, that you have to tell. Now here current acceleration is there, that is why this is false. Change direction, again this is false, this is fully false. So option D is incorrect. So option A is the correct answer. You got it? Why B, C and D are incorrect? Current acceleration is not seen in your whenever you are driving. Current acceleration, you cannot see the current acceleration, so that is why this is false. And why this is false? Because whenever you are your action would be turn the steering wheel or press pedals to change direction or change speed, right? Your action cannot be change direction and change speed. So that is why this is false. This is false. Okay, this change direction and change speed cannot be your action. Your action can be turn the steering wheel and press pedals. So that is why option C is your false statement. And option D, current acceleration is also false. This is also false, and this too is also false. So that is why option D is also false. So option A is your correct answer. Is it clear why it is not C? There can be a confusion regarding C, but C is not correct because change direction and change speed cannot be there. Okay, as your action. Your action can only be turn the steering wheel and press the pedals. That is why option C cannot be true. And option B and D cannot be true because current acceleration cannot be your state, because in a driving car you cannot see the current acceleration, you can only see the current speed through your speedometer. Okay, is it clear? I think it is clear to all of you.
It is clear. It is clear.
Yeah. Now, question number 9: which type of feedback does an agent in reinforcement learning receive? Option A is prediction, option B levels, option C cluster, and option D reward and penalties. This is
Sir,
again,
D. Rewards or
It is
penalties?
yeah, this is again a simple question. Everyone I think know this. An agent in reinforcement learning receives feedback. Okay, feedback. What is this reward and penalty? That this is nothing but your feedback. That you whenever the agent perform an action to the environment, this is the feedback from the environment back to the state. Okay, back to the agent. Okay, so this is the feedback. And what is this feedback? This feedback is in terms of rewards or penalties. Okay, so option D is the correct answer. Okay, so I hope this is clear. Now move to question number 10: which of the following measure best analyze the performance of a classifier? Option A precision, option B recall, option C accuracy, option D time complexity, and option E depends on the application.
So it depends on the
It
application.
depends on the application.
Yeah, absolutely right. It depends on the application because yeah, there is always a confusion. There is always a trade-off. Rather, you can say trade-off between accuracy and time complexity. Okay, so what happens is as you make the machine learning model complex, your accuracy increases, but its time complexity will also increase. So because of that, in real time process, what we want is our time complexity should be less as possible. Then only we can apply our machine learning algorithm to our hardware. Okay, if our time complexity is more, we cannot apply this machine learning algorithm in a hardware, and we cannot do this real time processing. Okay, so that is why there is always a trade off between accuracy and complexity. Like in some cases we prefer time complexity more than accuracy. In some case we prefer accuracy. Like if you are judging some medical problem, there what we do is we want more accuracy rather than time complexity, because accuracy there is I think more important. But time complexity, if you are playing some if you are making a machine learning algorithm to play a game or something like that, in that thing and that this game also depends on time, in that thing what we are more interested in time complexity. So that is why there is always a trade off between accuracy and time complexity. Also there is many times a trade off between precision and recall also. Like a cancer related problem or any medical problem, recall is what? Recall is true positive by true positive plus false negative. That means it determines the true positive out of actual positive cases. True positive, like recall, let me write it. Recall is nothing but true positive by true positive plus false negative, right? True positive plus false negative. So this lower thing, true positive plus false negative, is nothing but your actual positive prediction. Okay, and true positive is your predicted by your classifier or predicted by your machine learning model. So this is the true positive. Like now you are detecting the cancer, so true positive, it should be between true positive and true positive plus false negative. That means whatever your algorithm is predicting and whatever the cancer which is in true cases. So that is why recall in this case is more important. But like whenever you are doing something like spam classification, spam email classification, so their precision is more important. Precision is what? True positive by true positive plus false positive. Okay, true positive plus false positive. Okay, TP plus FP. So that is precision. In this case what you are doing is you are more concerned with number of true positive out of positive prediction. So how much positive prediction is there out of this, how much positive you are determining. So in this cases precision is more used. So that is the thing that the measure that we use to analyze the performance of classifier, that usually depends on the application. Okay, so generally accuracy is a term that we can use, or time complexity is a term that we use, and we generally do the trade-off. And in special cases we use the recall and precision. Okay, so that is the explanation for this. So I think no doubt in this because I think it is clear to all of you. So by this I am ending the session for today. Okay. So we will meet on 18. We will be discussing some of the question that we have discussed previously, and we will discuss some of the important questions, so that will be beneficial to you. Okay.
Okay, sir.
Okay. So by this I am ending the session for today. Okay. So yeah, everyone please download all those codes that I have made especially for all of you. In that code only you can there are comments in each step, so by seeing the comments only you will understand the codes. Okay, so download each and every code at least.
When will
And
be our next session, sir?
next session will be on 18, and that will be an extra session. Actually today's session is over, but we have to take an extra session that I will be keeping on 18. Okay.
18th is on Friday, sir.
Yeah, yeah, yeah.
The same timing, sir.
Yeah,
To
same timing. Yeah, you
oh,
can attend if you want. You can attend. Otherwise, you cannot also attend. Whatever you like. Okay. So it will be better if you'll attend. Otherwise, this recording will always be provided to you in that problem solving session for them. Okay. So with that, I am ending the session for today. Thank you all of you.